This video is about doing multiplication in different bases, that is, bases other than 10. First, let's think about what base 10 means. This really means that whenever possible, we group things in groups of 10. So we have separate symbols for 1, 2, 3, 4, 5, 6, 7, 8, and 9. But then if we add one more, we now have one group of 10 and nothing left over. We never actually see this many of anything. We always bundle or group this many together. So in reality, there is no new symbol for 10. It is really saying that there's one group and nothing left over. And we know that the one group is of this many. We'll represent this group of 10 with one of these. Then we keep counting up, and we exchange these units for tens every time we see them. Now when we have 9 groups of 10 and 9 units, and we add one more, what happens? We change the units for a group of 10. But now we have 10 groups of 10, and so we have to bundle those together. We can exchange them for one of these, which represents 10 groups of 10. We call this 100, but we write it as 100. This 1 represents one group of 10 groups of 10, and we have no groups of 10 and no units after the exchange. This is all familiar to us, and in some ways it's a little too familiar. After all, when we see this 10, we call it 10, but really it's one group of a certain size and nothing left over. But we think of it as its own amount because we are so used to the size of what it represents. Since we always group things in the same size groups, we have our units here, and then our tens, and then our 10 groups of 10, which we can write as 10 to the second power. And then here we would have 10 groups of 10 groups of 10, which is 10 to the third power, and so on. What happens, though, if we don't group things into bundles of 10, but we choose another number, such as 6? Then what would that look like? Well, we would go 1, 2, 3, 4, 5, and then when we have this many, we would say we have one group of 6 and nothing left over. This time, this piece will represent groups of 6 rather than 10. So we now see this, and we would write this many as 10. This number represents 6. Now we might read it as 10, but really it represents what we know in base 10 as the number 6. Then if we keep counting, we would have 1, 1, one group of 6 with 1 left over, 1, 2, 1, 3, 1, 4, 1, 5, and then 2, 0. Then if we keep counting, we would have 5, 3, 5, 4, 5, 5, and then what? We have 6 units, so we exchange for a group of 6. But then we have 6 groups of 6, so we group these together. Now we have one group of 6 groups of 6, no groups of 6, and no units. We would write this as 100. Just like with base 10, we can write our place values with exponents. Technically, they should look exactly the same since we don't actually have a number 6. But if we are thinking about this in base 10, we would have our units, then our groups of 6, then 6 groups of 6, or 6 squared, then 6 groups of 6 groups of 6, or 6 cubed, and so on. In other words, all the work is exactly the same, except instead of exchanging when we get to 10, we exchange when we get to 6. And the hierarchies work exactly the same way. The beauty of the Montessori Checkerboard is that all the work with the hierarchies is done automatically for us. Let's try to multiply two numbers in base 6 and see what happens. Here we have 342 times 52. Let's try this. Now we'll be doing the work mentally in base 10 because that's what we're used to, but then we'll have to convert to base 6 when we put our numbers down. We'll start here with 2 times 2, which is 4. Now we have 4 times 2, which is 8. But how do we write 8 in base 6? We write this as 1, 2, which is one group of 6, and 2 units left over. So here is what we'll do on the checkerboard. Notice though that we really weren't multiplying 4 times 2, but 4 groups of 6 times 2 because of the place value. This means we'll actually have one group of 6 groups of 6 and 2 groups of 6 left over. Now that can be a lot to think about, and when young students are working on hierarchies in base 10, that thought process is a big part of their work. But the mechanics become simple. We can just put the numbers down, and the colors and the place value kind of takes care of itself. Let's continue. Now we have 3 times 2. This is 6, which is written as 1, 0. So we'll put those numbers down as well. Now let's finish our multiplication with the second row. We have 2 times 5, which is 10, which we write as 1, 4. We have 4 times 5, which we know as 20, which is actually 3 groups of 6 with 2 units left over. So that is 3, 2. And lastly, 3 times 5, which is 15. But in base 6, we write that as 2, 3, since it's 2 groups of 6 with 3 left over. Now we'll add according to the hierarchies, so we'll slide all these together and see what we have for each hierarchy in total. For the units, we just have 4. For the 6s, we have 6, which we have to write as 1, 0, so we'll do that now. For our 6 squareds, we have 1 plus 0 plus 1 plus 1 plus 2, which is just 5. We have 7 6 cubeds, so that becomes 1, 1. That is one group of 6 to the 4th, with 1 6 to the 3rd still remaining. And lastly, we have a total of 3 6 to the 4ths. This gives us a final number of 31504 in base 6. Ultimately, it doesn't matter what base we use. If we did base 8, we would group things in groups of 8. If we did binary, which is base 2, we would group things in 2s. And if we did something in hexadecimal, or base 16, we would group things in 16s. But then, we need single digits for all the numbers up to 15. And to do this, we use letters. Counting in base 16 would look like 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10, or one group of 16 with nothing left over. Working with different bases can be challenging, but also very fun. And this work really helps us to analyze more deeply our current base 10 system.